In this video, we're going to learn about converting endergonic reactions into exergonic reactions. So reactions that left to their own devices would go in the reverse direction when we actually want them to go in the forward direction. So remember, reactions that go in the forward direction are exergonic. Reactions that go in the opposite direction, the reverse direction, are endergonic. And I want you to be able, after this, to explain the difference between the standard delta G and actual delta G. I want you to be able to describe 3 ways a cell can change an endergonic reaction such that it becomes exergonic. Explain how ATP is used to modify reactants. Describe the important difference between unphosphorylated and phosphorylated versions of a molecule, and explain why ATP is so widely used to modify reactants. So here I have a list of the 10 biochemical reactions that occur in glycolysis. These are reactions necessary to convert glucose into pyruvate. So in order for the cell to do this, each one of these reactions must be exergonic. Okay, otherwise, this wouldn't work. Some of them would be going in the reverse direction when they need to be going in the forward direction. But if we take a look at the standard delta G of each one of these reactions, sure enough, there are some that are exergonic, right? They have a negative delta G, but look at all of these. Even this one here, positive 23.8. All of these reactions that have a positive delta G mean that they are not exergonic. They are actually endergonic. They actually go in the reverse direction of the direction that we want. So how do we reconcile this? How do we reconcile the fact that clearly this is something a cell needs to do, turn glucose into pyruvate, but when we look at these standard delta Gs, it seems impossible. So let's take a look. That's really what we're going to focus on here. So the question is, how do cells convert reactions that are endergonic under standard conditions into exergonic reactions? And there's 3 basic ways that this can happen. And the first is changing the concentrations of the reactants and or products. The cell can couple the endergonic reaction with a more exergonic reaction. And finally, a cell can change the nature, the chemical nature of the reactant. So let's look at each one of these. So the first thing we need to understand is that the actual conditions of a reaction in a cell are different than standard conditions. And so we have a whole new delta G that we need to look at. It's this delta G without that little prime sign there, without that little degree sign there. This indicates that we are talking about the delta G of a reaction that isn't necessarily under standard conditions. And to figure out what that actual delta G is, you need to know 2 things. You need to know where that reaction wants to be, and that's the equilibrium constant. So when we look at the product of the products divided by the product of the reactants at equilibrium, that's our KEQ. That's our equilibrium constant. So this represents here where the reaction wants to be. It wants to get to equilibrium. Equilibrium is equal to KEQ. Now, if we take the negative RT and natural log of that, that's our standard delta G. Okay. So in order to figure out the actual delta G of reaction, you first need to know its standard delta G, its inherent nature, where it wants to be. And then what you need to know is, where is that reaction right now? What is the ratio of the products of the reaction to the reactants of the reaction? Where is it right now? So this represents where the reaction is. This represents where the reaction wants to be. This is KEQ, and this is called the mass action quotient. So once you understand that, you can look at an equation like this, and you can make some predictions. If Q is less than K, if Q is less than K, that means there are more reactants than what the reaction wants to be at. The reaction wants to be at a situation where it has less reactants than it does right now, which means that it has to convert those reactants to products. It wants to go in the forward direction. Reactions that go in the forward direction have a negative delta G and are exergonic. Okay, so if Q is less than KEQ, then we know we have a exergonic reactions at those actual conditions. Now, what happens if Q is greater than KEQ? That means that there's more products than what the reaction wants, right? The reaction wants to get to a situation where it has a little less products than that. So if there's more products, we want to turn them to get to equilibrium, we want to turn them back into reactants, which means we want that reaction to go in the reverse direction, which means we have a positive delta G, okay? So the reaction under those conditions where Q is greater than KEQ, we have an endergonic reaction. It will spontaneously go in the reverse direction as written left to right here. If Q is equal to KEQ, okay, if these numbers are the same, then that means at our actual conditions, they happen to be the same as the conditions of equilibrium. So we don't need to change the concentration of products. We don't need to change the concentration of the reactants. We are at equilibrium, which means we have a negative number that is identical to the positive version of that exact same number, and so our delta G is 0, and that's what we know. Delta G is 0 at equilibrium. So what that means is we have two delta G's we have to very much know the difference of. When you have a delta G that has the little prime sign there, the little degree sign there, you're talking about delta G under standard conditions. And under standard conditions, when you have 1 mole you start off with 1 mole of the reactants, you start off with 1 mole of the products, and you let those reactions run at 25 degrees Celsius, and you see where they end up. That is a very specific delta G under very specific conditions, and that's what you see here. And that's why you might see endergonic reactions here when you're looking at the standard delta G of glycolysis, for example, for reactions in a cell. But when you take a look at the delta G, and that means taking into account not standard conditions, but the reactions as they exist within the cell, and this is really important. Let's go down here. I know you guys never like to read figure legends, but it's really important to do so. If we read the figure legends, we see that, okay, delta G prime here, that's the standard free energy change. Okay, as defined in chapter 13, blah, blah, blah. But over here, delta G is the free energy change calculated from the actual concentrations of glycolytic intermediates present under physiological conditions in erythrocytes, those are red blood cells, at pH 7. So this is very specific conditions within an actual cell. The concentrations of products and reactants are completely different than what you would see here under standard conditions. And when you measure the delta G's under those conditions, right, the actual delta G, now take a look. Everything is either negative or pretty darn close to 0. So now, if they're negative or if they're really close to 0, it just takes some little shifts in concentration to drive that reaction in the forward direction and get it to go in the direction that you want it to go. So that is a very important distinction. Standard delta G actual delta G. So let's try a sample problem here. And we've got this reaction, and it's actually a reaction here that is the production of glucose 6-phosphate from inorganic phosphate and glucose. And what we're asking here is, what if we assume that the current concentration of glucose 6-phosphate is 0.001 molar? What is the minimum concentrations of glucose and inorganic phosphate? What are the minimum concentrations necessary to get this reaction to go in the forward direction, to get the reaction to be exergonic? And what we're given about this is that the standard delta G is positive 13.8 kilojoules per mole. With that information, let's solve this problem. I would recommend that you pause here and you try to solve the problem on your own, and then take a listen to my solution on the next slide. Okay, hopefully you just got finished trying to solve this on your own. And believe me, you'll be better off for trying it, even though you may get it wrong. So this is the trick. What we want to do is we want to figure out, well, at equilibrium, when this is at equilibrium, what's the concentration of glucose in inorganic phosphate when G6P, or glucose 6-phosphate, is at 0.001 molar? That's what ultimately, the key to understanding this is figuring out what these concentrations are at equilibrium. Okay, how do we do that? Well, we know that the equilibrium constant is the ratio of the concentration of products over the concentration of reactants. So if we can figure out the equilibrium constant, then we can figure out the concentration of glucose and inorganic phosphate. How do we do that? Remember this reaction, or this equation here? The standard delta G is equal to minus RT, the natural log of the equilibrium constant. So that means the equilibrium constant is simply E to the minus standard delta G divided by RT. RT is, right, the gas constant and temperature in Kelvin, and I've given you a little cheat sheet here. That's 2.479 kilojoules per mole. By the way, yeah, okay. So we know that the ratio of the products to the reactants is 0.0038. So, and we know that we have an equal ratio. Our stoichiometry here is 1 to 1. So we know glucose and inorganic phosphate concentrations are going to be the same, so we'll call them X. When we plug and chug here, we get 0.0038 equal to 0.001 divided by x squared. Solve for x squared, and that means you get that the concentration of glucose and the concentration of inorganic phosphate is 0.513 molar at equilibrium when we start off with G6P at 0.001 molar. So at equilibrium, this is 0.513 molar. This is 0.513 molar, and this is 0.001 molar. You need 500 times the concentration of glucose and inorganic phosphate than glucose 6-phosphate to be at equilibrium. That's crazy. That's why this reaction is so endergonic. So what that means is if you just add just a little bit more than 0.513 moles of glucose, just a little bit more than 0.513 molar inorganic phosphate, you'll drive that reaction in the forward direction. Okay, so basically the answer to the question is, as long as you add more than 0.513 molar glucose and inorganic phosphate, you can drive that reaction and convert it into an exergonic reaction. Okay, the next way that we can convert an exergonic reaction into an endergonic reaction, let's flip that around. The way we can turn an endergonic reaction into an exergonic reaction is by coupling, reaction coupling. And what that means is here's the reaction that is endergonic. It's that same reaction that we were looking at before. Glucose plus inorganic phosphate yields glucose 6-phosphate. And we want to go it in the forward direction, but the problem is it has a positive 13.8 kilojoules per mole. It's going to go in the reverse direction. We don't want that. And we already found out that in order to if we wanted to change the concentrations, we'd have to have 500 times the concentration of glucose and inorganic phosphate to get it to go in the forward direction. And that is just not something a cell can do. So a cell has to take advantage of something else, and that's this reaction coupling. And so the way that works is you take a reaction here that is endergonic, and you run it here with, or you couple it to a reaction that is more exergonic than this reaction is endergonic. So let's couple this reaction, okay? Now you can only do this, you can only couple reactions that share an intermediate. Do these two reactions share an intermediate? They sure do. Inorganic phosphate here, inorganic phosphate here. So let's draw out that coupled reaction. So here's the solution. First, we need to write out our coupled reactions. So here's the first reaction. ATP yields ADP plus inorganic phosphate. We are hydrolyzing that ATP. And then here's our second reaction. We are adding an inorganic phosphate to glucose to make glucose 6-phosphate. Now this is our reaction that is very exergonic, more so than this reaction is endergonic. And that is the trick. Because to figure out then the delta G of this entire reaction going from ATP to glucose 6-phosphate, what you do is you simply add the delta G's of each of the reactions together. Plus 13.8 plus negative 30.5 gives us negative 16.7 kilojoules per mole. And as long as when you add those two delta G's together, you get a negative number, that coupled reaction is exergonic and will run in the direction as written. If it gave you a positive number, it would run in the opposite direction as written. Okay? So, when you want to couple two reactions, they have to share an intermediate. And they have to, when you add up their delta G's, they have to have a negative delta G that will tell you that reaction is running in the forward direction as you write it. The last thing, the last way in which we can take an endergonic reaction and convert it into an exergonic reaction. And this depends upon you having that very fundamental understanding that we kind of on a very simplified level think of delta G as the energy in the products minus the energy of the reactants, which means as long as the energy of the reactants is greater than the energy of the products, we'll have a negative delta G, and that reaction will be exergonic and run in the forward direction as written. So what that means is sometimes we have a reaction. If we want to take glutamate and add an amino group to it to make glutamine, if we look at doing it this way, it's endergonic. Glutamine has too much energy such that the reaction goes in the reverse direction. So our third way of changing that is by chemically altering the reactant such that it has more energy than it did before. And one really good way of modifying reactants is by phosphorylating them. So if we phosphorylate glutamate, and we'll talk about phosphorylation in a second, what we'll have is glutamyl phosphate. Now that has much more energy in it because phosphate is that big, giant, clunky functional group with two negative charges on it. It has much more energy than glutamate, such that now this reaction right? When we see this reaction here, there's more energy in the reactants than there is in the products, and now this reaction is exergonic, okay? So if you change the nature of the reactant such that it has more energy than it did before, you can drive that reaction in the forward direction. You can make it exergonic. Now, ATP is most commonly in a cell the thing that is used to phosphorylate reactants. And this is what ATP looks like. So here's our A of ATP. ATP means adenosine triphosphate. This is our adenosine. Our triphosphate is 1, 2, 3. And what we're doing is we're transferring that third phosphate group from ATP onto other things. And as a result, ATP becomes ADP, adenosine diphosphate. So here is what we have. If we try to take glutamate and directly add an amino group to it to make glutamine, Endergonic won't work. Instead, what the cell does is it first uses ATP to phosphorylate glutamate into this enzyme, this glutamyl phosphate. So there it is, it's phosphorylated right there. These are the two molecules, right? Glutamyl phosphate versus glutamate. Glutamyl phosphate has a lot more energy than glutamate, such that now this new reaction here that we created is exergonic, okay? And notice, right, we've added an inorganic phosphate, there it is, and then when we turn this into glutamine, we've just gotten rid of that inorganic phosphate. That shows you, that demonstrates that inorganic phosphate has nothing to do with the structure of glutamine. The sole purpose of that inorganic phosphate that came from ATP was to essentially activate glutamate, to make it a better reactant, a higher energy reactant, to make it more reactive. For those of you who remember your organic chemistry, what phosphate is, it's a great leaving group. It makes this reaction exergonic because phosphate is such a good leaving group. Now, ATP, like some of these other videos that you watch, is kind of like the battery of the cell, that it's constantly being used to phosphorylate stuff, and when it does so, it increases the energy of those things, and then it needs to be recharged. It needs to have a phosphate group added back on to that ADP to make ATP. We'll get to that a little bit later in the course, but for now, why is ATP so good at phosphorylating molecules, of transferring its phosphate group onto other molecules? And the answer is that the hydrolysis of ATP to ADP and inorganic phosphate is very exergonic, negative 30.5 kilojoules per mole, which means you can couple this reaction to the phosphorylation of all kinds of molecules, and when you add those two delta Gs together, when you couple those two reactions together, oftentimes this negative 30.5 is going to be greater than how exergonic the other reactions are. Now, why is the hydrolysis of ATP so exergonic? There's a lot of reasons. The first, and probably the easiest to understand, is look at this. 1 negative charge, 2 negative charges, 3 negative charges, 4 negative charges, all close to each other. That's electrostatic repulsion. It's almost like this last phosphate group is just spring-loaded, ready to pop off. And when it does so, an inorganic phosphate, and that's what you see here, is stabilized by resonance. And when you stabilize a product, you make it more likely for that reaction to occur. The reaction I mean is the hydrolysis of ATP. So that's 2. Number 3, the proton release. So the ionization. So here we have a hydroxyl group on the ADP, one of the products, and it drops off that proton, and that, again, that stabilizes, that proton release, that ionization stabilizes the product and therefore makes that reaction more exergonic. And finally, mass action. There simply isn't that much inorganic phosphate and ADP concentration within the cell. When you lower the concentration of products, you're driving that reaction in the forward direction, making it more exergonic, more negative delta G. So ATP is very good at being hydrolyzed, which means it's very good at phosphorylating other molecules for these reasons here. However, let's take a look at something. Here is the delta G of the hydrolysis of some other phosphorylated molecule. So here's ATP, about negative 30.5. And that's greater than glucose 6-phosphate and glycerol phosphate, which means you can use ATP to phosphorylate glucose, use ATP to phosphorylate glycerol. But look at these molecules, 1,3-bisphosphoglycerate, phosphoenolpyruvate, phosphocreatine. The hydrolysis of the phosphate groups from each one of these are all more negative delta G than ATP, which means you can couple a transfer of a phosphate group from, let's say, phosphoenolpyruvate to ADP to create new ATP. That is a very important source of ATP in the cell. By using these high energy phosphorylated molecules to themselves phosphorylate ADP, creating ATP. That is called substrate level phosphorylation, and we are going to learn a lot more about that later in the course. So, please review this lecture until you can, with confidence, explain the difference between standard delta G and actual delta G. Describe 3 ways a cell can change in endergonic reactions such that it becomes exergonic. Explain how ATP is used to modify reactants. Describe the important difference between an unphosphorylated and a phosphorylated versions of a molecule. And finally, explain why ATP is so widely used to modify reactants.